Python notebook. Okay, so hopefully, right? So hopefully, after this session, you would be ready for session 2, in which we are going to work on network data. So I was told by Professor Heru that you are actually going through operation research course. So this is one part of operation research course, right? So in operation research, you do see network data. For example, transportation problem, in which transportation problem is converted into a network, and then we try to find, for example, shortest path from one point to another, right? So in session 2, we are going to look at network data, and then we are going to do machine learning on it. We are going to do topological data analysis, extract the information, shapes information, and then use for machine learning or operational research. Okay, so today we're going to just concentrate the theory part of topological data analysis. Okay, this is an example of a graph, right? So a graph in a formal way, we represent as a set of vertices and edges. And this graph here is a weighted graph. So every edge has a weight. So you can see we have nodes from A to F, A, B, C, D, E, F. And then we have weights connecting these nodes. Okay, with the edges connecting with nodes with weight. Okay, so the first question is that what structure do you see? Yeah, what structure do you see from this graph? What structure do you see? Anyone? Anyone want to try? It'd be nice if you can interact and say something, yeah, so that I know you are following. Anyone? What structure do you see from this graph? Example of a structure would be a loop. Yeah, a loop. A loop simply means, like, you see, this is in fact a loop. Yeah, you can even consider this as a loop and this loop. So you can even say a graph. This graph has 3 loops. 1, 2, 3, 3 loops. Or in a simple way, we say holes. Yeah, the first hole, the second hole, and the third hole. Okay, that is the structure actually. And then all this, imagine now we have one extra node. Let's say we have H. Node H is not connected at all. Then we can say there are actually 2 components. The first 2 component, H itself, the rest of the component which are pretty much connected is the second component. So the structure here we can say in terms of connected components, number of components. And then, as I said, the first time around, the loops, yeah, or we can also call holes. So we have 3 holes. We have actually 1 component. If we were to add on H here, then we get 2 components. So normally, where do we see this sort of weighted graphs? These graphs can be in the form of, let's say, friendship network, in the form of a transportation, in the form of, like, for example, the connectivity of train between cities, and so on and so forth. Okay. Okay. Now, how about point cloud? So for point cloud, we can also similarly try to figure out the structure of its data. For example, the first data set here is we can see there are 2 blobs. Yeah, one cluster very much in this on the left-hand side, whereas the other cluster is on right-hand side. Yeah, so there are 2 components actually. Yeah, 2 components. You can see 2 components. But is there any loop here? Is there any loop? In fact, maybe there is. If we connect them together, we connect some with lines and all that. we might see small loops deep inside in this cluster, right? Whereas if you look at these two noisy circles, two noisy circles with some sort of a Gaussian noise. Yeah, so there's one huge loop and the other huge loop here. In fact, if you were to draw, there is some sort of like a noisy loop here also. So some sort of like 3 loops. And then if you were to discuss in the context of a component, there's just one component. Everybody tend to be like together, right? Okay, so that is the first data. And then the third one, this is very much a random point cloud, random points, yeah, in 2-dimensional space. So basically just random, right? But again, if you were to join, for example, like that, if you were to join points like that, we do see some sort of like holes, right? Some sort of holes. And if you were to discuss in the view of components, maybe like they are very much random component. Okay. So the main idea is here is that how do we join the points? How do we join the points such a way that I end up getting the structures information? Again, I would like to repeat the structure here, the form of loops and also components. Okay, so the main idea of topological data analysis is that the methodology to extract this information, loops and components, okay? So how we do it is that first we need to construct a simplicial complex. You can think of simplicial complex, yeah, constructing simplicial complex simply means is that connecting lines, and then if the 3 lines are connected, then they create a field triangle. Then of course we can just move on. If a four points join together in a 3-dimensional shape, then we can get the tetrahedron and so on and so forth. So that is actually simplicial complex. Yeah. So if you have a point cloud, or even if you have a graph, to extract the component, the information of component and loops, we usually need to go through a simplicial complex so that we can easily extract those structures information. Of course, creating simplicial complex has a certain rule. Okay, so let's look at those construction of simplicial complex. Okay, so simplicial complex itself has a dimension. For example, a point is written, it's just a simple bracket like that. It's a 0 simplex. So a collection of points would be, we would be able to encode a 0 simplex. So let's say this is V0, we have another one, V1 here. Then the collection would be V1, comma, V0, right? So that is 0 simplex. Whereas one simplex are 2 points joined with one edge. This is one example of an edge, which is a 1 simplex. Whereas a 2 simplex is a filled triangle. As you can see here, it's filled, right? So a filled triangle is written as V0, V1, and V2 in a bracket. So it's a three points, right? And then a 3 simplex is a tetrahedron, which now we have 4 points joined together, not just with few triangles, rather it is also the volume is also filled. Okay, so a point is actually a subset. A point is a subset of a simplex, and then also a 2 simplex is a subset, and then this is also a subset. So it goes like that. So without having point, we will not be able to create 1 simplex. Without having 1 simplex, we will not be able to create 2 simplex. Without having 2 simplex, we will not be able to construct 3 simplex. So a 3 simplex, the face of 3 simplex are 2 simplex, 1 simplex, and 0 simplex. Okay, so again, we say the face. The face basically the lower building block of a simplex. Okay. Now, so now let's say we have a simplex which contains, of course, this is a field triangle ABC, and then an edge, and then we have 2 points DE. So this is CD, and then we have D and E, and then we can imagine A, B, and C. Okay, so this is the, let's say a student says this is a simplex that he or she has. So the question now is that, is it a proper simplex, right? Is it a proper simplex? So let's assume that our data, we can construct, a student has constructed such a way, one, 2 simplex, and then one simplex, and 2 0 simplex, right? So this, in fact, cannot be a simplex because remember, this A, B, C, it's being a 2 simplex, must have A, B as 1 simplex, A, C, B, C, right? And then also, these are all, of course, 1 simplex. And then it must also have 0 simplex. Okay, so what it means is that this simplex, sub-simplex are missing in this simplex in which a student has built. All right, so that is actually a simple term or condition to create a proper simplex. So if you have, you need to have all the faces of the higher simplex such a way that it becomes a proper simplex. Okay. Now, from simplicial complex, the idea of creating simplicial complex is that to extract a connected component, also to extract number of loops. Okay. So now, in order to encode, for example, let's say we have, yeah, okay, and in order to encode such a simplex, okay, let me assume this is our simplex, simplicial complex, and we want to encode number of holes. So number of holes and connected component. So connected component, number of connected component, or we call it as B0. I shouldn't say B, I say Betty 0. So Betty is actually a number which encodes connected components. So the first is Betty 0. So Betty 0, the answer would be 1 connected component, 2 connected component, and then the 3rd connected component. So Betty 0 will be 3. So another one would be, as I said, loops. How many loops are there? So rather than asking how many loops, we ask what is Betty 1? So Betty 1 basically represents number of loops. So here, what would be Betty 1? So Betty 1 here, we know there is 1 loop here, only 1 loop. There is no other loop anymore. So Betty 1 would be 0. Okay, this is a simplicial complex when we have now successfully extracted connected component and loops being the structures information. Now we can also do extract those information from a well-known mathematical objects. For example, a line, this is just one line or one edge or one simplex, but T0, which represents number of connected component, would be 1. Betty 1 represents number of independent loops, would be the holes. For example, for a circle, Betty 1 would be 1. Similarly, for an analyst, there's one hole in the middle. So Betty 1 still will be 1. Whereas, of course, we know Betty 0, a circle is just one unit circle. I mean, one circle, just one annulus here. Whereas here, for this mathematical object here, we have 3 disks, disk 1, disk 2, disk 3, in which we now get Betty 0 as 3. Of course, this has no holes. So Betty 1 would be 0. Whereas for torus, of course, it is just one connected component. Torus, you can think of a donut, right? A donut which is hollow. Okay? That is a torus. And then Betty 1, for torus, in fact, there are actually 2 type of holes. The first hole will be the circumference of the donut, whereas the other one would be in which goes around the donut. Okay, so that is why we get Betty 1 as 2. Whereas Betty 2 is, there is hollow inside, right? As I said, you have a hollow donut, which is called a torus. So it would be 1. So similarly, we would be able to, let's say you have a graph like that. Yeah, you would be able to calculate the number of connected components, which is one component here, another component here. So you have 2 connected components. Whereas for Betty 1, I have 1 hole here, the second hole here, the third hole here, right? So Betty 1, I have 1, 2, 3. So that is for graph. So basically Betty, of course, we can go for higher Betty numbers. Yeah, for example, if you go to Betty 2, and then it encodes the third dimension of your whole, yeah, the higher dimensional whole, which we call as void. Okay, so these Betty numbers, we would be able to extract from point cloud or even from graph data once we, of course, once we construct the simple cell complex for point cloud. And for graph data, we can also directly extract. We will see how we would in the next coming slides. Okay. Then there is also another measure, right? For example, we measure our weight based on, for example, based on kilogram or pounds. We measure the distance maybe with kilometer or meter. Previously, we measured with Betty numbers, right? We measured connected components and nth dimensional whole with Betty n, right? So Betty 0, Betty 1, Betty 2, and Betty 3. So another way of encoding this shape information other than Betty number would be Euler characteristic. So Euler characteristic, yeah, Euler characteristic, now previously we used beta, representing a Betty number. Now you use chi to represent Euler number. So the Euler characteristic is just an alternating sum of Betty numbers. Yeah, alternating sum of Betty numbers. Or for simplicial complex, we can also encode Euler's characteristic by doing summation, alternating sum again, based on the number of simplical complex for a given dimension. Yeah. So K0 represents number of simplical complex of 0th dimension, whereas K1 here represents number of simplical complex of dimension 1, and so on and so forth. So again, for simplical complex, we can reduce the equation further by saying that it is just an alternating sum of its building block. Okay, this is example. So assume we have a simplicity complex in which we have connected them, constructed them at this stage now. Of course, we have points. Some points are by itself. Some points are joined together, creating triangles, which is a field triangle. And then some are just like one simplex connecting with just edge, points connected with edge. So if we were to calculate, we were to calculate the calculation of Betty numbers and Euler characteristics would actually encode shape information, right? So let's calculate Betty 0. how many Betty zero simply means how many connected components are there in this simplicity complex. So one simplicity complex, like here, it's like very much like everything is connected. This is one. This one, it's one point itself would be another component. And then finally, this one component here below. So that is why we get Betty 0 as 3. So Betty 1, of course, the loop, there's only one loop here. Probably at some point, if we were to join, this loop would appear. But currently, there is no such loop. So this one loop here. Of course, we don't have voids. Yeah, it's just two-dimensional space. We don't have voids. Therefore, the Euler characteristic of chi, right? We do an alternating sum of all this three. Yeah, Betty 0 minus Betty 1 plus Betty 2. So the Euler characteristic of this simplicity complex is 2. Okay, so that is the idea of topological data analysis actually. Now we want to extract this, right? So how to extract? Before extracting them, first of all, let's look at what is the idea of topological data analysis. So the main theme of topological data analysis is data has shape, shape has meaning. For example, every human being, you and I, we have a thumbprint, a unique thumbprint which represents us, right? So using this unique thumbprint, we would be able to differentiate between two individuals. So similarly, we can take the shapes information for a given point cloud or network or graph data and differentiate them. Okay, so the main idea that you saw earlier is Betty numbers, and then chi representing Euler characteristics. Okay, so the motivation of TDA would be first, we would not just investigate at a local the point of the data, we want to look at the overall the solution of the data, right? Not just at one point, rather we want to look at the whole, we want to extract the whole shape of the data, right? And TDA is well known for resistant to noise. If you have missing data, TDA still will be able to capture those Betty numbers and all that characteristics. And when we talk about topology, yeah, so TDA here, it is invariance under deformation, which means if the data has somewhat like distorted shape, we would still be able to capture Betty numbers and all that characteristic well, right? And then TDA out there, we do not need to calculate by hand because we have a Python packages available, yeah, open source, in which we can just call and use to extract these information. There are actually two methodologies for TDA. The first one here, so imagine now you have this point cloud in two-dimensional space. Of course, this point cloud can be in any dimensional space. Two-dimensional space easy, we can just plot it out and visualize. If it is in 100-dimensional space, you will not be able to visualize. That is when you want to use the TDA engine on the right-hand side, which is called a mapper algorithm. What does a mapper algorithm do? Basically, it would take the input would be, so for example, the point cloud here, you can push it into mapper algorithm, you will get a graph, yeah, a graph, a collection of vertices and edges connected to represent the structure of a point cloud. You would then be able to do, for example, exploratory data analysis to understand well about your data, right? That is the first methodology. And the second methodology would be persistent homology, right? So what it does is that when you push this point cloud, this particular point cloud, the output would be a diagram. And this diagram is known as persistence diagram. So this persistence diagram, it would encode the birth and death of this connected component and also loops, okay? For example, yeah, so this x-axis represents the birth of a component, whereas the y-axis represents the death of a component. We will be using a scale parameter. So as we increase the scale, right, at some point, there's a birth of this point, birth of this hole actually, this hole in the middle. Yeah, this hole in the middle actually encodes this point, whereas the bigger hole encodes this point here, right? So at some scale, right, we get the birth of this small hole, and at some value it died, whereas the bigger hole, it persisted over time, where the death of the second big hole here is higher, right? So what we get is that the birth and death of each hole, which represented by blue, whereas the rate points represents the H0 or Betty 0. Okay. Remember, Betty 0 represents connected component, and Betty 1 represents the holes in your point cloud. Okay, so the output for persistent homology, which is on the left-hand side, is a graph. Yeah, we denote this graph, or we call this graph as persistence diagram. Yeah, again, the word persistence. We are trying to represent all those components which persisted over a scale, right? We'll see in a while what is a scale. Now, what is actually persistence diagram? Persistent diagrams are just a collection of pairs. Yeah, first pair and second pair and third pair and so on and so forth. A collection of points represents those information of the shape, or again, Betty I, right? Okay. So now another important information from this piece, this persistence diagram, is that the further it is from this diagonal line, the more persistent it was, the bigger hole it is. Yeah, the blue points here. Yeah, so you can see the shorter ones are a smaller hole, right? So the birth value minus the death value would be the lifespan of a given topological information here, the whole. Okay. All right. Now, why topological data analysis? Right. Of course, for classical summaries, you would be able to probably compute the mean of point cloud, the variance, correlation, the standard descriptive statistics, or you can even compute the regression coefficients, maybe try to draw with represent with the function, right? Or you can get the clusters, and also you can get distance-based similarities. But these are the things that usually we do. Whereas for topology data analysis, what we're asking is that how many components are there? How many connected components are there? How many holes are there? Which feature persists over a scale, right? Which is a noise, right? So these are the things that we would be able to answer with topological data analysis, specifically persistent homology. Now, as I said earlier, we are going to use a scale. And we're going to use a scale in order to connect them together and extract the information of topology, which is Betty numbers and Euler characteristics. So we can increase the scale, right? For example, here the scale is represented at T. We can increase the scale, and at each scale, we can get one simplicial complex. Right? And remember about the phase, right? So if at x2, right, those phases would be in the previous dimension, right? So as we increase the T, we get a different type of simplicial complex in which we would be able to capture the information of the shape, which is H0 represents the H0 represents the collection of Betty 0, H1 represents the collection of Betty 1, and H2 represents the collection of Betty 2. All right. So as we increase the scale, we would be able to get the pairs, birth and death pairs for each subsimple complex actually. Okay, so now let's do that. So now the idea is that now I have a scale. Now how I would be able to draw simple complex out of the scale. So there are many ways actually. One way is we use Victory-Rieps complex. The idea of Victory-Rieps complex, or in short, we call it just Rieps complex, is that when we at every point, we give a ball cover. This is a ball. So the ball has a radius. Yeah, there is a radius. The radius, in fact, we denote as t. So t would be our scale, right? As we increase the t, and we keep track who is overlapping with who. For example, these two balls are overlapping, so we can now join them together with one edge. Similarly, these two balls too are overlapping, so we can also join them together with one edge. Whereas these two here, there is no edge. As we increase the ball, so now these two edges are also touching. Now we have three triangles joined together. So then we can fill the triangle to get two simplex. And this here is just one simplex edges, right? Whereas here at D0, it's just zero simplex, just points, right? So as we increase, of course, there's no more changes anymore, right? So now as we can keep track from left to right, we can keep track the changes of Betty 0 and Betty 1. So for example, for D0, Betty 0 was 3 connected component. Betty 1 was just 0, no holes. At some point here, for here, I mean, at D equals to, 1D, Betty 0 is, all of them are connected. So just 1. Betty 1 is still 0. There's no hole yet. For 2D here, Betty 0 is still, of course, they have become 1. And Betty 1, there is no hole. It's a filled triangle. So Betty 1 is 0. Same goes to at here. Yeah, it's a two-dimensional simplex. Okay, that is a simple way to understand how we can scale over to look at not just at the point, but rather to see how they are related to their neighbors. Okay. Now, there's another way also. Check realization. Check is rather different, right? So you see here, even though we have a triangle here formed at 1D, but still it is just 1D because the triangle did not, the balls did not overlap. 3 balls must overlap in order to create a field triangle in which we get at 2D. Okay, that's differences between check simplex. We have so many simplicities complex out there actually, so many types. Yeah, another type would be alpha complex. Alpha complex, we do Rieps complex, but we only create the triangle based on Delaunay triangulation of the points, right? So it is, of course, we can only do for lower dimensional data set. It is not proper to do a higher dimensional data set due to Delaunay's computation cost. Okay, now let me show you a simple demo of doing filtration of this point cloud. Okay, now you see this is the 3 points you saw. So if I were to use Victory-Rieps, so I can increase the scale. Yeah, as I increase the scale, right, when they touch this Victory-Rieps complex, then no more, just 1. Yeah, originally it was all 3 components. Eventually they join together, create simple complex. Okay, we get until up to two-dimensional simplex. Can do the same thing with check. I guess you can see for check simplex it's slightly different. Oh, there you go. For alpha complex, okay, so I should draw the Delaunay triangulation first. This is the Delaunay triangulation, it's not edge. So you can see when it overlaps, it's this, I mean, two balls must overlap on top of each other. Only then it creates edges. And then all three must overlap in order to fill the Delaunay triangulation, which is the triangle. Okay, so these are the ways we can create simple cell complex. And again, we can, as we increase the scaling factor, which is here the radius, as you can see, we can keep track of Betti numbers. Of course, a collection of Betti numbers, the alternating sum of Betti number, in fact, would be Euler characteristic. So now Betti 0 is 3. When they overlap, Betti 0 now becomes 1. All three of the points are connected. Betti 1 remains a 0, right? Till the end. Yes, this is an example. Okay, for the data set you are going to see in a while, right? In fact, you saw two noise circle data set. So we can do the same. Yeah, we can keep on increasing. We can keep track of Betti numbers. Yep. Okay. All right. So that is a short demo. Let's go back to our okay, so this is our okay, let's go back to our slide. There's three data sets, right? Okay. So we can do to these 3 point clouds and extract those Betti numbers. And then those Betti numbers, which we can then represent it with persistence diagram, can be used for machine learning. Now, let's move on. Let's see how I can extract persistence diagram. So now, by now, you know, filtration simply means is that we increase the scaling, here the ball radius, and then we keep track of the Betti number, the changes in Betti numbers, which is actually can be represented in a persistence diagram. Okay. Now, so in persistent homology, right? So we keep track of birth and death. And remember, lifetime simply means death minus birth. So for the vocabulary wise, so which feature appeared, which called birth, whereas death, which feature disappeared. Persistence, or we call as lifespan, is death minus birth. Long lifespan means it stayed for a very long time over this radius increase of radius parameter. And then short lifespan means it can be noise, which means the whole is like did not persist at all, right? Okay, so now let's look at this two circle data. Okay, this is two circle data. First, how many connected component would be there, right? So as we increase the size, the radius ball, remember the parameter scale, we would be able to extract the components. We would be able to extract the loops. Yeah, of course, we have two loops here. And then we can also see the strength of this each loop, right? Okay. This is exactly what you will get. So this is persistence diagram. Yeah, persistent diagram basically, yeah, we denote as D is actually a collection of pairs of those features. The first feature, this is the first feature, the first hole, a second feature, second hole, and then all these points in rate are actually H0, which represents the connected component. As we increase the radius scale, it will get connected and connected and connected. Of course, at one point, everybody will be connected and Betti 0 will be 1. So it goes up to infinity. As you increase, there won't be change anymore. Everybody's connected, just 1. Okay. Now, we are going to extract those Betti numbers, and then we are going to plot persistent diagram using a package called Guti. right? So for example, here we have two most persistent H1, which encodes Betty number B1, Betty1, sorry, would be 2, yeah, first pair and then second pair. If you were to count the lifetime of each pair, just death minus birth, you get its lifetime. Or we can also call it lifespan or persistence. And it's basically the further it is from the diagonal line, the more apparent or the more persistent it was over this parameter R radius. Okay. Okay, there are also short lifespans which are very much close to the diagonal line here. They did not, I mean, it was very fast. They died, they gave birth, it was given birth, and then it died equally fast, but very fast. So you can call it noise, right? Depending on the type of machine learning that you are doing, you can call it noise. At this moment, we can just call it noise. Okay, so the idea is that taking persistence diagram, we can convert into persistence vector and then do some sort of classification work or regression work, which is very much a machine learning work, right? So what it means is that persistent diagrams already encoding the shapes information. Taking the shape information as it is not really proper because machine learning wants a vector which can differentiate between 2-point cloud, for example. So here, each point cloud would represent a persistence vector, which is as though it is representing its thumbprint. Okay, thumbprint would be unique for each type of point cloud. So the idea now is that, so you first, of course, you have some sort of question, you collect your information, and then you do the cleaning of your data, and then you might want to push it into mapper algorithm to do exploratory data analysis to look at the shape to understand better about the data. Or you might want to push it into persistent homology, you extract the shapes information, right? And then use that shape information, just like a thumbprint for each of the data, and then do machine learning, yeah, to modeling. And then your machine learning model would be able to get, of course, using feature engineered, which feature engineered here, basically the shape information. You create the model, and then you can then test your model and deploy. Okay, so rather than taking point cloud as it is and pushing into the machine learning and creating a model, rather we just use the shapes information and create model. So that is the whole idea of creating machine learning for example, prediction. Okay, so first go to vector. I would like to repeat again. If you look at this persistence diagram, so we know persistence diagram is just a collection of points of Betty 0 and Betty 1. Then using this persistence diagram and pushing it into machine learning, of course, we can do that, but machine learning likes vectors. These vectors, you can think of it as thumbprint for each data, right? So in this form, persistent diagram, it is not easy to just push it into a vectors. In fact, if you look at here, there are no vectors around here, right? No vectors around, I mean, no points around here. So which means, right, around here, which means this space is not a well-defined space, right? We want a well-defined space, a well-defined vector, such a way that when we push in machine learning can learn in a proper way. So in order to do that, we will take persistence diagram and then convert it into a vector. For example, Betty number, right? So as you can see, this is a Betty 1. As I keep on increasing, right? At some point, there was a one hole appeared. After some point, a second hole appeared. And then the first hole died, became 1 again. And then over some period, it just persisted one hole until the big hole also died. Right, so this is actually, we're keeping track as we increase the radius, we keep track the changes of Betty number, and that would be called Betty curve. So Betty curve basically just a collection of points, which is a long vector, right? Long vector. So this long vector can be parameterized such a way that to any number of points that you want. For example, I want 80 points, so there are going to be 80 points on this curve. Now, this 80 points would represent one vector. Similarly, for persistence, in order to get persistent landscape, yet another type of vector, what you do, you take this persistence diagram, you rotate it 90 degrees. After rotating 90 degrees, you draw a tent function, just like a camp. Right, of course, everybody gets a tent function. Let's not take H, just take the blue points, H1. And then you identify the maximum layer by layer. So the first layer, let me just color with yellow. The first layer would be this layer. The second layer would be a green layer, which is a small second highest layer, and so on and so forth, right? So this is called persistence landscape. Yeah. So the first layer, this was the second layer that I explained earlier. The first layer was in yellow. Yellow. Oops. Yeah. So here we extracted three layers. The third layer, in fact, just zero. It's a collection of zeros. Okay. So again, this is yet another way to vectorize the persistence diagram. Okay. So another way to vectorize persistence diagram is called persistence image. So taking 2 points here, this is the big or the small circle, this is a big circle point. And then at each point, we give a Gaussian, like a blob, and give a value to it. Yeah, this value can be the lifetime's value. Lifetime basically means death minus birth. And then that would be the intensity for that particular pixel. Again, the idea was I rotated and then I give value for that particular pixel with the lifetime value, and then I give a Gaussian distribution around it. So all those pixels gets the intensity based on these values. So this is called persistent image. So these are three types of vectorization from persistence diagram. So these three, in fact, represents the shape information of our point cloud. Okay, we can do the same for graph data. So for point cloud, I would, for point cloud, whatever that you saw, we can actually do for graph as well. Okay, so that is our next work. Let's assume we have a graph now here. Now, for graph, we do filtration differently, right? For point cloud, each point gets one ball with radius r, and r being the scale. We increase the scale and we keep track of Betty 0 and Betty 1. Whereas for graph, we keep track of the weight. Yeah, for graph, we keep track of the weight. Okay, so let me just draw on top of this. Let's say for parameter scale t equals to 1. So I'm going to choose parameters t equals to, first, of course, 0. If parameter equals to 0, I'll get all the nodes. Parameter t equals to 1. This edge appears, this edge appears. So A, B, and C will get connected. Right. When parameter t equals to 2, this A, D, and D, C will get connected. The rest of parameters, the rest of the edges are yet to appear. So at parameter t equals to 2, we are already getting a Betty 1 equals to 1. And parameter t equals to 3, Betty 0 is already 1. Everybody is connected. And Betty 1 is still 1. There's only one hole, right? When parameter t equals to 4, this edge appears 2. Now we have 2 holes, right? When parameter t equals to 4, we have 2 holes appearing, and where t1 represent, stay as 1 already, it's going to persist as 1 forever, right? When parameter t equals to 5, this edge appears, AC appears, thus closing closing the triangle on top and closing the triangle below as well. So we end up having one Betty 1, which would live forever, right? Will probably live forever because there is no more edges for us to increase in order for it to appear and close this C, A, B, C, D, B, C, E, F. This hole will be there forever. So in fact, that is how we do persistence. It is how we extract the information from a given graph data. Okay, so as I said earlier, so this is the filtration. Yeah, in fact, this is one picture actually. Yeah, it's too close to each other. You can't really see the picture. So this is one picture at t equals to 1, t equals to 2, t equals to 3, t equals to 4, and then finally t equals to 5, right? So you end up having just one hole. At some point here, we have 2 holes. Yeah, Betty, 1 was 2. Eventually, 1 was killed. So we just end up with Betty 1 equals to 1. Of course, we can represent this in graph data. Yeah, this 1 point. I mean, this 1 point represents the one hole. This point here, which is at infinity, that hole never died because there is no edge to close that hole. So this is how it works, okay, for persistence diagram for graph data. In fact, yeah, for graph data, we can eventually do the same. We can keep track of Betty 1, and then this is actually, this is how we keep track of Betty 0, the orange line here actually. So the Betty curve, yeah. So this is a persistence landscape for Betty 1, and then persistence image for H0, H1 actually, the holes, yeah. We can also keep track of the connector component as well. Okay, now next, we're almost done with 1 hour, right? So next, we're going to do this. Yeah, we're going to try with point cloud. We're going to try with graph data. Of course, we need to train and we're going to split train and test. For test, we are going to take out some part of the data, and then we are going to test whether it can do classification properly or not. Well, so we're going to create with persistent homologies extracted features, persistent homologies extracted vector. We're going to train it, and then of course we're going to do a model here. Using this model, we are going to evaluate with the test taken out data and see how good persistent vector can model, can differentiate between 2 or 3 types of classes. Okay, so we're going to do this data set. Yeah, we're going to like simulate number of this type of data, this type of data, this type of data, and then we're going to put them together. And then of course each has its own label. The first label will be 2 blobs. Next label is 2 circles. Third label will be random cloud. The fourth label would be 2 moons. So the model's job is that when I give any type of this data, it should be able to clearly say, oh, it is 2 classes, 2 moons, or 2 blobs, or random cloud. So that is the job of the classifier. Okay. So now let's do the Python code. Okay, so please open the Python code. In case if you don't have, I also put it in Google Drive. Yeah, you can always you can share in Google Drive. I mean, share the link. And is the okay? I'll share in the chat box also if in case you are yet to get it. Actually, you should have got it from Prof. Heru. Okay, so I'm going to share in the. There you go. So that is actually in Google Colab. You know, if you did not install in your machine, then you can just go to this Google Colab and have a look at it. In fact, what I've done is that I've also made it into a PDF file. This is a Python notebook. Yeah, I have actually um, printed in a PDF file. I have also posted in Colab. So please go and get it, and we will go through this now. Okay, so I'm going to explain. The output is there actually, but I'm going to explain to you what each code does. Okay. So please open up. Do you have any questions? If you have any questions before we proceed, please ask now. Any question? No questions? Okay. Feel free to ask me. Yeah. If you have any questions, feel free to ask me. You can stop anytime. Stop me anytime and ask me. I have no problem. Okay, so I hope everybody can see. Now let me share. Okay, so whatever that I showed in the lab, I mean in the lecture, right? So we are going to do it with the Python code now. All right. Okay. The first part, of course, is going to be point cloud. We're going to use a point cloud to extract information. All right, and then from that information, of course, we are going to use persistent homology to extract the shapes information represented in the persistent diagram, and then convert into persistence vector, pH vector, and then eventually we will use for machine learning. The last part would be a short demo on machine learning for the 4-point clouds that I said earlier, right? Before doing that, I mean, before doing machine learning, I'm also going to give you that example that I shared in the lecture on graph data. So we can also do filtration on the graph data in order to get or to extract shapes information. Okay, all right. Now, first of all, I'm sure you need, of course, you need some packages to run this Jupyter notebook. The packages are NumPy, standard package, of course, scikit-learn, standard package. Scikit-learn we will be using for machine learning purpose. And Guthi, Gudhi, this is the package that we're going to use to extract that information, persistent homology. Yeah, the machinery of persistent homology is actually in Guthi. And matplotlib, pandas, and networkx are just those secondary packages that you need to run this by Jupyter notebook. Okay, so to install, just run this line. Of course, I have. So of course, it will say that everything is. I mean, in my machine, everything is here. Right. So in your machine, make sure you have as well. Right. You can run if you don't want to run in your machine, you can always go to Google Colab that I shared in chat and run there. Okay. So everybody's okay. If I think the only thing that it will start loading would be Guti. The rest of it, I'm sure you are familiar with. Okay, I hope everybody is in the same page. So once you have your packages installed, you can then run your code. Let me reduce the size a little. Okay. Now, this first cell, for this first cell, I have actually commented a lot of information on my my Jupyter notebook. Your Jupyter notebook will look like just this. Okay. Okay. So make sure you copy this, yeah, like that, and then create a new cell like that and run. And then that will install all the packages needed. Once you have the packages installed, you can then run the code below. The first part here, we are just extracting, getting all the packages in this Jupyter notebook. Yeah, especially this part here. From Goody, yeah, once we import Goody, from Goody, we are going to get Betty curve, persistent landscape, and persistent image. These three functions would actually vectorize our persistence diagram. Goody itself would run the Victory's RIPS. We're going to run RIPS, and then we're going to represent it. And we're going to get a simple cell complex. From simple cell complex, we're going to get persistent diagram. We're going to vectorize persistent diagram using Betty curve, persistent landscape, and persistent image. Okay. First is point cloud. First, we would just create point cloud. Yeah, we're going to create three types of point cloud that you saw in the lecture. 2 noise circles and 2 blobs. Yeah, this is the noise circle that we define on top. And then finally, so some random point cloud. Yeah, we call it random point cloud. This is a random point cloud. Yeah, X random. So when you run, yeah, this is this definition to create that noisy circle, and then the next definition is to create the rest of the point cloud. So 3 types of point cloud. Okay, 3 types of point cloud. So for persistence diagram, we are going to try for 2 circles point cloud. Okay, 2 circles point cloud first. So here, so we have chosen 2 circle. You can select either 2 blobs or random cloud and then run. So it will run for you. But now so feel free to change later. Now we will run for 2 circles first. And later you can try for 2 blobs and random cloud. So for 2 circles, first, yeah, so we have created here a definition, a function, a short function, which would return simplex tree and then the persistence pairs. Yeah, the pairs. Yeah, the pairs for the point cloud. So if you see here, let me just increase the size. This is the heart and soul of persistent homology. Yeah, first get the Goody. We got our Goody in by calling GD actually dot Ripser complex. We're going to create a Ripser complex for a point cloud called X. Yeah, X is the selected point cloud here on top. Then the maximum edge that is a radius, the maximum radius that you want to increase the size of the ball. Okay. And then the maximum dimension. And once you create the RIPS, you will get the simplex tree. Yeah, create simplex tree. So the maximum dimension you want. If you just want edges, the simplex just be if you want, and H0 would be until just the connected components. H1 you will be get up to the Betty 1 values. Yeah, Betty 1's basically at the holes. Okay. H2 you would get up to white. You can also get whites. Okay, whites for 2-dimension complex. Okay, so once you get that, then you can extract the persistence. So here st.persistence would extract all those information, all those pairs actually. So when you run def compute underscore rips underscore persistence, you would get a simplex tree and then persistent pairs. So of course we can print out those persistence pairs and have a look at them. or we can even plot it. Yeah, we can plot persistence diagram. Okay, and then we want to like extract each interval out because we have H0 H0 represents connected component, H1 represents those loops or holes. Okay, all right, so yeah, please run. So this is what you get for two circles. Oh, you can always change and get for random data set and also two blobs. Okay, so we see that one, the smaller hole, and then the bigger hole, right? This is a persistent diagram that you get. Okay, so you have about total about 160 intervals, 160 pairs. Finite intervals means 159 pairs minus this one infinity pair. Remember, infinity is not a number in which we can encode into a proper vector. So that's why we always remove that infinity point, and then we convert into our vector. And then H1 longest lifetime would be 0.32. So this point here, this point, 0.332, that's the longest lifetime for H0, sorry. Whereas for H1, the longest lifetime is 1.2937, which is this point here. Okay, so those are lifespan. Okay, next is converting into persistence vector. So once you have your persistence diagram, those pairs, you can take that pairs and then push into those Betty curve, persistent landscape, and persistent vector. Before pushing in, we want to remove if sometimes we get a empty pair. So if empty pair, we want it to make it 0, 0, 0, 0, 0 as a pair, right? And then we also sometimes have that, remember you saw that infinite pair, we need to remove that infinite pair too. So this def finite or dummy would actually capture that either you just end up not having any pairs or infinite pairs. We want to remove infinite pairs. So basically this cell would clean up your pairs such a way that later on it is ready for you to push into persistent vectors function. Okay, so once we push those pairs, yeah, for H0 dimension 0, H1 for dimension 1, so we name them as H0 diagram and H1 diagram. So we are then ready to push into our vectors, persistent vectors. First is Betti curve. So Betti curve, we can set the resolution as I said. I want a longer resolution, of course, more finer it would be. I want here the resolution to going to be 80 points, right? And then here I'm just using the function fit transform. So this pass goes into Betti curve and I get that curve. Right? Similarly, for Betti 0 and also for Betti 1. Okay. Then I have landscape. So for the Thyssen landscape, first the number of maximum layers that you want. Here I set the maximum layers I want would be 3, and I can also set resolution. So when you set all these 3, you can then fit transform and then push your H1 pairs. So here, as you can see, I'm just pushing H1 pairs. I'm not pushing H0 pairs. It might not be interesting, but you can also do that. Yeah, here I just choose H1 pairs. Finally, for persistent landscape, same thing. This time around, I have a number of option as well. First is the bandwidth. The bandwidth, how intense, the bandwidth would be how dispersed the Gaussian value is, right? So you reduce and increase. The next is the weight. The weight for each pixel would be based on here x1 is the death value, x0 is the birth value actually. So I want the weight based on the lifespan. You can change anything that you want actually, but here this is what we set with. And then the range, the clip, the birth value from 0 to 2, the death value from 0 to 2. And then the resolution. I want pixels 40 by 40. And finally, I push into the usual way, feed transform to get my vector. Okay, so you can run that. Yeah, show. And below, the setup would be just creating the 3 plots. Plot 0 representing Betty curve. Plot 1 representing persistent landscape. Plot 2 representing persistence image. Persistent image, we are using image show function from matplotlib. Persistence landscape, a persistent landscape, we actually just plot using a plot function. And this k function is actually just the by layer. By default, it will be a long strip curve. Now we're just breaking it into layer, the first layer, second layer, and third layer. So it will get its respective colors. That is the for loop here for. So if you shift enter, okay, so this is the changes of Betty number over the parameter scale radius. So at some point it went to 1, and then another second hole. Over some time, the second hole just persisted over some time because it's a huge hole, remember? Okay. Okay, and then the first layer, and second layer, and third layer. Now blue, yellow, and final layers in green. And then this is the persistence landscape. Okay. Okay, we have now 3 types of vectors out of our birth and death pairs from persistence image. Similarly, we can do for the graph. Yeah. For the graph. Okay, so I'm creating the graph data here. So A, B, C, D, E, F are the nodes. And then I'm also adding A, B, for example, giving the weight 1, BC, weight 1, and so on and so forth until AC, weight 5. In order to visually see it in a nicer way, I'm just giving the coordinate for each node. Of course, this is not necessary, but just to visualize nicer. Okay. And then the rest, we're just using network X. Yeah, we're using network X to draw the graph. Okay. Well, these are just to label the nodes, the weights, and give colors. So when you run that, you see that this is a graph that we saw in our lecture. So far, okay? So we can then continue. Right now, we can do filtration over this graph. Right? Remember, the filtration is basically the increment. The scale now would be the weight. Okay. So for weight, right? So weight, remember, we're just going to keep track of the weights. So if based on by keeping track of the weights, we would be actually just identifying those edges that with that particular weight, and just keep on adding to the graph, and finally we get the whole graph, original graph, right? So that is the idea. So here we're actually doing that. Yeah. First creating an empty graph that adds some, with that particular weight, we're just going to keep on adding to the graph based on the weight, right? So this would be the active edge. as we increase. Okay. And then finally, we get the graph. And just that I mean, it is pretty long because I'm trying to show the filtration. Usually we don't really, I mean, once we know for understanding purpose, we look at the filtration. When we do real work, we don't really look at filtration. Rather, we will straight away get the persistence diagram. For example, here, now we have to like set up for the code so that it would, for example, here it would create those three triangles which would be, filled with orange, right? Okay, this is that particular code that fills the triangles A, B, C, and A, C, D. Okay. All right. So this is the code. Then you get to see how from t equals to 1 until t equals to 5. So this is the filtration that we would go through. But in real, we do not do that actually. We will straight away create the complex. Yeah. So for example, here we name it as graph underscore to goody underscore click underscore complex. Okay, so we straight away push in here in this function to create the complex. How the complex is created is that, again, just using the simplex tree, right? So we will keep track of the index of the node and the index of the each edge, and we will just keep on increasing the t, the weight t, and then we will just keep on inserting in the simplex. Finally, once you have the simplex, right, you can, once you have the simplex, of course, this definition, you see the input is G, the graph, the filtration would be the weight, and then of course, for graph, it's just maximum dimensions 2. The output would be the simplex tree, and then these are just the nodes to integer and integer to node, the reverse, so that we can later keep track who's coming in and who's going out, or who's dying. Okay, so this now, okay, so we push into the function earlier, our weighted graph with the weight that we have stated there with the maximum dimension 2. Now, this is the tree that we get from here. Okay, this is a tree that we get, and then we push it into persistence. Yeah, in Guti, so you will already obtain all the pairs, persistent pairs. So once you get the persistent pairs, the rest are just cleaning up and then getting a persistence diagram. Oops, I did not run the previous function, I think. Okay, so here the rate points, you see all the changes of Betty 0, right? First was we had Betty, when t equals to 0, we have 6. Betty number is actually 6. Yeah. Betty 0 is actually 6. Yeah. 6 of them appear already at 1. At 1, 2 appeared. So this this rate point is actually 2 on top of each other. Okay, this is a multi-set. A persistence diagram is actually a multi-set. There are 2 points on here, and then at 2, and then at 3. After 3, you see no more changes at least. Everybody become 1 until the end. Okay, until infinity. So the birth of the first hole, or first loop is at 2, and it died at 5. And then the next loop, the birth was at 4. It never died because there's no more edge in the original graph. Okay, so if we go up here, as you can see, the birth of the first hole at 2, it died at 5. The second hole birth at 4. Of course, it never died because, of course, there's no edge connecting or closing this hole. Okay, so once you get that persistence diagram, you can use the same thing what we did for point cloud to convert into a persistence vector. Yeah, so we have H0 and H1, and same thing. First, clean up, yeah, and then push into petty curve or petty curve, persistent landscape, and persistence image. Okay, again, you can see the petty curve here, how it changes over the increment of the weight. All right. Okay, so these are the signature, these are the shape information of this graph. Right. Now, next is a mini demo. Right, so mini demo on using collection of point cloud with different shapes. We're going to do a classification work, and then we're going to predict. Okay, we're going to predict after creating a model from a training data set. We're going to predict given a point cloud what it is. There are 4 classes. Okay. Oops. Okay, so class 1 is two blobs, class 2 is 2 circle, and class 3 random cloud, finally class 4 2 moons. So we are first, of course, we create the data. Before creating, we just want to look at some sample. So I'm just going to collect some sample out and then plot it. Okay, these are some samples for each class, 4 classes. Okay, that 4 classes, we are also going to see the persistence tree type of first get persistence diagram, create persistence diagram, and then after that, I'm going to extract persistent landscape. Once I get persistence diagram, so let's go one by one. So first is creating persistence diagram. After getting persistence diagram, I'm actually saving H0, connected components information, and H1. Then once I have H0 and H1, I'm already splitting them into train set and test set. The splitting size is 30% goes to test, 70% goes to training set. Okay, so H0 train set, H0 test set, H1 train, and H1 test. Okay, so we're doing with H0 and H1 information. All right, and then using this information, we're going to create Betty curve, Betty 0 and Betty 1, persistent landscape 1, which means we are going to just extract the information of the whole for persistent landscape building. Also, we are going to use H1, now Betty 1 information for building our persistence image. Finally, we're going to take this train set, we are going to put them together next to each other, concatenate these long vectors. First is 80 resolution, next is 80 resolution. Oh, here we are using 60 resolution only. So 60, 60, 60. I'm going to just put them together and create a long vector. And this X string fit, yes, the long vector would now represent as my input. So I'm not putting my input, the point cloud inside for train, rather I'm using this persistence vectors information. Okay. So Betty 0, Betty 1, persistent landscape, and persistent image. Similarly for test set, yeah, I've set up like that. So here we are already breaking them into two types, to test and train, so that there is no leakage. The model will not learn from test set. Okay, and then, okay, so this is our training. This is a training feature matrix. So our matrix is a pretty long matrix, yeah. So this is for testing. So I have about 196 point cloud, and I have about 84 point cloud for testing. And then my concatenated vector is about 465. Yeah, all this adding up of 60, 60, 60, 60, and then 60. I have two landscapes, so it's going to be 120 here. My resolution per persistent image is just 15 times 15. Yeah, 15 times 15 is a pretty huge number. We're going to flatten this persistent image and then concatenate. That's how we get 465. A long lengthy vector. So of course we can, I mean, what we are going to do, this is the um, framework, yeah, point cloud. We push in the Reeves complex, and then we get persistence diagram. And then for persistence vector, we concatenate, not add, concatenate. There's added the add function, that add symbol represents concatenation of all those vectors, yeah, in which we get a for lengthy vector, Betty, landscape, and persistent image. And then we're pushing into random forest. Random forest is a type of classifier. Create a model. Once we have a model, then we will test with our test data. We build with train data. Okay. Okay, here we are just extracting some of it. Yeah, sample indices, extracting some, and just have a look at all those vectors. So Betty curve, for example, this for the first row is for two blobs. This is how the Betty curve looks like. Yeah, and then Betty curve 0 represents connected component. Betty curve 1 represents the loops. And then H1, the landscape. And then H1, persistence diagram. If you compare the one below, the row below is for two circles. You can clearly see the differences in Betty 1 in landscape H1 and also in H1 persistence image. So if you can clearly see, of course, the machine would be able to clearly discriminate between these two types, right? Rather, for Betty 0, we can't really see the differences. There is, but we can't see much. So imagine we concatenate all these three to create one signature for each point cloud. Yeah, so if you go below further, you see a random cloud with just random, yeah. So there are clear differences. And this the last one will be for the moon, two moon shape. Yeah. Okay. You see the differences. Okay. All right. Okay. Is there any similarity between all this? Oh, looks like. Let me reduce the size a little. So just that we can see the differences. Okay, no, still huge. Let me reduce further. Okay. Now, if you look, there is some sort of similarity between random cloud and two blobs. Yeah, see the two blobs with the Betty 1 curve, the random cloud Betty 1 curve. There is some sort of similarity, and also for H1 landscape, even for H1 persistent image. Yeah, there's some sort of similarity, but the rest should be okay, right? If you were to look at back those two blobs and random clouds, somewhat looks similar. But of course, visually it's not. It's in two-dimensional shape, so we would be able to visually see and check. Okay. Now we do classification work. So we are going to push into random forest. For random forest, it's basically the building block would be decision tree. So I'm creating 250 trees. Okay, and then it would then take the majority vote, right? So this is the model building. They're pushing the train set, and then I'm going to check the test set, and I'm going to see the confusion matrix in the report. Okay, so we have about 84 test set. Okay, of course, as you can see here, the precision is perfect. Yeah, 100% classification of 84 set. Yeah, 84 point cloud. Each point cloud, random point cloud, 2 blobs, 2 circle, 2 moon were classified in a perfect manner. Okay, so as you can see, each has about 21 point cloud. Each did very well. Yeah, so there is no true positive or true negative. Yeah, so on the left hand side, you can see true label. Yeah, below predicted label, 2 blobs, 21. 2 blobs predicted also 21, exactly as it is. Right, of course you want to compare, right? So if you want to compare, just if I take the point cloud alone, I push into machine learning, what would happen? Right, I did that for comparison's sake, so that you can see the differences. Right, of course, it's the shape-wise, it's perfect, right? So now if I take this point, pairwise distance between the point clouds and see now push into machine learning. So here I'm creating a function for pairwise, and then the same I'm going to take the same point cloud and push into machine learning. I mean, the same set random forest, the same random state. See to what extent it can do prediction. Okay, so if you see here, if you just push the point cloud alone, right, without extracting the shapes information, you will see there are some sort of true positive and true negative. For example, for random cloud, yeah, 5 of the random cloud were classified as 2 moons. Yeah, and then for 2 moons, 14 2 moons point cloud were classified as random cloud. So there is a mixture. If you were to take just point cloud as it is, take the distance and then push into machine learning, you can clearly see there are the drop of for random cloud, it's just 63% of F1 score. Yeah, 2 moon very bad, 42% only. The accuracy of F1 score, the accuracy really fall. Yeah. Okay. So if you were to compare between these two, right? So for baseline, the one that without persistence vector, it did so about 77%. Yeah, whereas if you extract the shape and then you use it, you can clearly see it did in a perfect. The model performed perfectly 100%. Okay, so that again, that would be the concluding remark here, right? So we can see, if I were to go back to my notes, the importance of the shapes information, right? Okay. So to wrap up here, yeah, we can see I can just go back here. Oops. Okay. So we used point cloud today, right? And then we split train then test set, right? Of course, we use persistent diagram. Yeah, we have your train state. We extracted for train set, and then we also extracted for test set. And then we vectorize it. We use Betty curve. Yeah. we use Petty curve, and we use persistence landscape, and also we use persistent image, right? Of course, we did for the same thing for test set also. We extracted them, and then you use all this information, and we built our model. This being the information of the shape of the point cloud. And we build the model, we use random forest with the model. And eventually what we did, we got 30% of test set. Yeah, we kept it aside. And then we did the pipeline is the same. And then we did testing. As you can see, if we were to take the point cloud as it is and push it into, of course, break it to train test set, same set actually, and push it to classifier, you would see the performance is pretty low, 77%, as you compare to persistent homology's features. Okay, so that shows the importance of persistence vector, which encodes the shape information. Right. So next week, I mean not next week, the next session, we would work on more on network data. Okay, so we would work on more on network data and see how we can actually use the shapes information to do those kind of machine learning. Right. So that is for next session. So here again, I would like to remind you, right? So next week, next session, first we will go through exercises. So make sure you do all those exercises. We'll discuss the answers for exercise for session 1, and then we will move to session 2. And for session 2, we will focus on network data and see what are the things that we can do to do, for example, for do machine learning, and see what extent the shape information itself would be able to increase the accuracy. Okay. So that would be the end of my session. I mean, me talking. If you have any questions, by all means, please ask me. If you have any doubts, please ask me. Or you can even email me if you want. Yeah. My email is here. Yep. This is my email. I'm actually, my name is Gobi Tasan. Rudrasamy is my father, actually. Okay. So, any questions? You have any questions for me? Yeah, 15 minutes. Any questions? Please ask me.
Okay, thank you, Dr.
Gobi
Gobit
Tasan.
Hassan.
Yes.
Yeah, okay. Sorry. I say thank you for that comprehensive and engaging presentation. Your insight on research of operation research provided not only valuable knowledge but also practical perspective that we can relate to our studies and research. Okay, before moving to Q&A, I'd like to invite participants to share any thoughts or key takeaways, either by unmuting or in the chat. Feel free to contribute it on a quick comment. Okay, now we'll transition to the question and answer segment. Okay, guys, if you have question for Dr. Gubit Hassan, please raise your hand in Zoom or type your question in the chat box. Okay.
No questions. Anyway,
Okay.
if you don't have questions,
Okay,
it's
guys.
fine.
Okay,
Yeah.
please feel free to raise your hand and
Yeah.
type your question in the chat.
Yeah. But what very important would be that please go and do the exercise so that we can, okay, in the exercise for the questions, I also put marks there, right? So if you see the exercise, this is the exercise. Yeah. So I put marks there. So once you do the exercise next week, next session, you can mark together as we discuss, and see what mark you get. Okay, that would actually reflect your understanding, so that hopefully you'll be ready for session 2. Okay. Okay. So, and also try to think in the context of operation research. Yeah, because you're doing operation research for this course, right? Think how would a filtering graph, a graph, for example, which represents, okay, for example, here, this question, right, a university model campus shuttle network with weighted graph. If I were to filter, right, if I were to filter it, if I were to extract the information of the shape, what and how would I be able to use that information to solve a particular problem? Trying to think that way, right? So anyway, now if you have questions, feel free to ask me.
Okay, because if there are no questions yet, I'd like to ask a question on behalf of the participants. Okay, so between vectors, ribs, and chess complex, I mean, how
Yes.
do we choose with with to use for a data set, and what impact does it have on the resulting pH features like that?
Okay. Oh, I like that question. Okay, so you see, I will show the, I'll go back to the, oh, sorry, I'll go back to the demo, right? Let me show the demo. A very short answer would be using, okay, let's take this one. Yeah, this is the, this is the data. I should draw the ball. Okay. No, okay. Okay, this is a data set, right? Just a collection of data set. In fact, I did not use the whole data set we saw in the lecture. Rather, I just chose a collection of it, and to see, to show you how over the increase of the scale radius, we get to see the complex, right? So this is Rips complex. The equation Rips complex is very simple, right? Whereas check complex. Okay, so if we, to compare, we should go here easier. Okay, for check complex, right? 3 balls must overlap to create a filled triangle. It's computationally expensive, right? Whereas you see the hole here, there's hole in the middle, right? There's a hole in the middle regardless all this, the increase of the radius, which really encode there's a hole in check complex. Whereas for rib complex, the hole is closed even though there's a small hole inside. So ribs is an approximation of check complex. Check is very expensive, computationally expensive. Ribs is cheaper. So if you have a huge point cloud, you should use ribs. And now people have created a better ribs, means a better way to compute ribs in a more less costly as compared to the old ribs. Okay, and then alpha complex. Alpha complex behaves somewhat like ribs complex, but actually we are using Delaunay triangulation. We are not creating a simplicity complex. Rather, we are based on the Delaunay triangulation. We're going to extract that edges, and we are extracting the triangle created by Delaunay triangulation. This is the best actually, but Delaunay triangulation itself, it's expensive. For more than dimension 3, it's not easy to produce a Delaunay triangulation. Since that's the case, if your data is in dimension 2, dimension 3, you should use alpha complex. But beyond that, cannot. Again, for RIPS, as I said, for RIPS, you can use any type of data. It's an approximated version, and it really encodes well as well. Okay, so hope that answers your question. Did I answer your question? Is that clear?
Okay, yes, thanks, Dr. Gobit Hasan. I like it. And one more question, if you don't mind.
Yeah, please go ahead. Any number of questions, fine. Yeah.
Okay. Like when we have point clouds that are very spread out or messy, sometimes sometimes the software shows little loops like that aren't real. They're just noise. I want to know how to handle that in Python so that the persistence diagram only show the important loops and ignore the fake short life ones like that.
Okay, for that I will go back to I will show one example and then try to explain from here. For example, here, right? This is not okay, for this point cloud that you see on top. This is actually a two-dimensional point cloud. Okay, and this is the exact persistent diagram that you get. Okay, so even though you see there are as you increase the size, I mean the scale, there are small holes will appear here, right? There might be like small holes appear here. As we increase the scale, small holes appear here. All those small holes, yeah, are the ones that very much near to the diagonal line. So you can actually do a thresholding. Thresholding simply means is that, okay, right? If now you know that the lifespan, yeah, lifespan is actually the death value minus the birth value. So when the lifespan is very huge, you know it is a persistent feature, persistent hole. If the lifespan is short, not so persistent. So by taking that thresholding, for example, lifespan, okay, a lifespan less than or equals to uh, 0. Let's say 3, I would ignore. Ignore, right? So the simple thresholding like this. So which means lifespan greater than 3, I'm going to take it as important feature. By simply thresholding, you would be able to differentiate already. So I've seen people do this sort of model. For example, people have done for breast cancer, thresholding. A simple thresholding like that would be able to differentiate between those MRI image with breast cancer or not. Yeah, this is an example. So you can think of different ways. So the idea in persistent homology, research in persistent homology is to think of different ways how to use this type information to do a better accuracy as compared to the traditional machine learning method. Okay. I think you are muted.
Oh, sorry. Okay. Yeah, I get it. Thank you for the answer, doctor. And since there are no question again, we will now close the Q&A session. And before we officially close, I want to say thank you again to Dr. Gobit Hasan. And we would like to take a moment for a quick photo or screenshot documentation of today's session.
Okay. So
Okay.
I will stop sharing, yeah?
Okay, doctor.
Stop sharing. Okay.
Okay, Stefanus, we like to take a documentation. So guys, if you don't mind, please open your camera so we could take a
Okay,
documentation today.
wait a minute ya, Cia.
Okay.
Teman-teman yang mau on cam boleh on cam dulu aja.
Okay. Oke, mungkin bisa kita hitung aja ya, Ste.
Oke,
Okay,
boleh.
I'll count it. 1, 2, 3. Take a photo, please. Okay, once again. There's any pose? Like what? Gimana pose-nya, Nel?
Freestyle.
Oh, freestyle. Okay, let's. Okay,
Oke.
1, 2,
One, two.
3.
Oke.
Okay, thank you. Once again, we sincerely thank you to Dr. Gobit Hasan for sharing